Hi, my name is Sahasra. So today I'm here to present you about my final project that I have done for ADTA5560 repairing neural networks for sequential data. So first, I have taken a data set named monthly beer production in Australia, which has data from 1990 1956 January to 1995 August over a 4 decade data we have here. So in this project, it is focused on time series of monthly data regarding beer production in Australia. To carry out a detailed study on this, the file contains historical production records, the date from January 1956 and ending in August 1994, the offering a control database of an outstanding record for over 37 years. And the dataset structure is notably clean and well organized, featuring two primary columns, a month indicator as a factor variable consisting of the month of the number and total beer output for every month in million liters. As all values were present and there are 476 monthly variables including in the dataset, it can be better fit time series analysis for forecasting tasks. And these figures can be assumed to be from the Australian Bureau of Statistics, from where it is a source of our dataset, and it offers great potential of trends, decomposition, and investigation for seasonal variations. So, or next we have taken a simple RNN to create sine wave data. So for this, we have taken 10,000 data points and a Gaussian noise is added to this. And by by creating splitting the data points into training and testing, we have created sine wave uh, from the data. From the data points. In order to attempt the identify sequential data patterns, the first approach, we have used a simple RNN model, and in which we initially trained a sine wave data, which is constructed so that they perform a specific pattern. This data set included 10,000 data points. Similarly to the previous experiment, and used a Gaussian noise. It was introduced on purpose to mimic real-life data fluctuations, in which, in line with the standard practices everywhere in the field of machine learning, we have divided the available data points into 8 is to 2 ratio, which is 80% for training and 20% for testing the data. 80% 8,000 data points for training and 2,000 data points for testing. The model architecture was deliberately designed in 3 levels, and it helped us to capture time related patterns. The structure of input layer is to Carter for time series data and with the shape of none, comma 1, simplifying freely variable sequence length with one feature. This was succeeded by simple RNN layer consisting of 10 units, specifically set of identify temporary patterns in the data. And the last layer, which was fully connected, had one neuron and it was output for regression. The total and trainable parameters were collected and calculated. and these calculated points were 131, and it is offering a reasonable model capacity, wha- and also barely avoiding the illusion of unnecessary patterns. And a four-wave 44 images were used in the dataset for the training process, and the training process was performed for 100 epochs. The Adam optimizer and mean square error are used as a optimizer and loss of function respectively. This configuration was indeed beneficial. Training error was 0.10 and validation error was 0.015. It, it is signaling as a good generalized of the model with no or negligible overfitting. And the model displayed a good fit with the ratio of predicted and actual value being generally high, even the noises were observed in the data. However, we can find some differences that were identified in the border of the uh, RNN, and it is mainly caused by the sensitivity and inability of a simple RNN architecture, and this will handle long-term dependencies. And for visualization of simple RNN, we have a broader view of model performance through the epochs. The training as well as validation loss were wrapped over epochs, and this indicated that the loss reduced for the training process and the loss curves for validation. So it also followed the same trend. One of the plots was to provide side-by-side comparison of true and predicted sine waves on the test set, that it is demonstrated how the model effectively captured the structure of sine. Observations for a sine RMS model was to learn characteristics of sine wave and generalize fairly well and noisy sets, but some discrepancies in predictions were observed, maybe because of noise sensitivity and the nature of simple RNA. Thus, for the purpose for further enhancement of this approach, less evolutionary changed architecture as LSTMs and GRUs could be used as they are more adapted to learn temporary dependencies in time series data. Next, we have LSTM neural networks. Here we need to explain about vanishing gradient problem. So, vanishing gradient problem will occur during back propagation phase in the auto-associated neural networks. More specifically, it happens current neural networks. This arises when the gradient or partial derivatives which are used when updating the model's weights are very small. In other words, the weights receive a very little update, making it difficult for network to learn. This becomes worse in RNNs when handling long sequence issues and can be mitigated by extending sequential issues. While transforming gradients through the multiple times, there is a magnitude reduce gradually causing the model to fail in detecting the dependencies over sequence. The practical impact is significant. The updates reaching the layer forming early layers of the network are negligible. There is a problem while capturing long-term dependencies and learning rate either shows right down or stops. And next we have exploding gradient problem. So basically, exploding gradient problem is opposite to vanishing gradient problem. Exploding gradient problem is gradients that tend to excessively large during backpropagation. This introduces impression if excluded at the customary training data during the training data process, especially When the training profile networks or long sequences exploding gradients and learning rates are increased rapidly, and model weights will become very large, causing them to exceed the numerical scale. Imagining and thus making the training process either very unsuitable or simply not possible. Collectively, these gradient problems cause a serious disruption to learn more sequential data by network. Next, we have simple RNN limitations. So there are some crucial drawbacks in simple RNN architecture, which seem to the process of sequential analysis. The first drawback in long-term dependencies is the network cannot operate with information that is more distinct from the current input and thus cannot use information for earlier in a sequence effectively. The network has a short-term memory model, more precisely described by hidden state at each time, which is insufficiently developed to contain and work with information over time. The deficiency is most felt where there is need of consolidated information and for later time. The architecture is also figured. The architecture also experience gradient instability problems such as vanishing and exploding gradients with the depth of network increases or when applying it on sequences. The second issue of concern in simple RNN is computational complexity. It's computationally expensive as the RNN is forced to recalculate information for each step in the sequence. Additionally, this network exhibits high recognition of initialization since its accuracy depends on initial weight values and slow convergence could be observed as poor learning results. And we have LSTM solutions. So after all such limitations were the specific design for LSTM network due to integrate architecture, this was developed to counter the problems. The main advance is their getting mechanism, and this has three vital parts. Um, Parameters to forget gate, and the forget gate defines which information from the previous cell state should be erased. In other words, remove unnecessary data. The input gate decides which information has to be allowed inside the cell, and the output gate decides the cell state what information should be used at a specific time step. Together with the gating system and the cell state, a specialized memory component LSTM are capable of keeping selectively modifying information through outshot sequences. So the importance of LSTM and simple RNN is more apparent. Their input-output memory interfaces are improved, enabling them to be fixed long-term dependencies, which would be unwound in simple RNN. The change level via controlled gradient flowing through the cell state ensures the vanishing and exploding gradient issue will not affect the training process. The LSTMs prove to be superior for tasks that require processing long-term memory and sequence related, where the learning happens more effectively and generalized. The architecture is also better suited for sequence inputs of arbitrary lengths, which makes it more applicable in real-life scenarios. These features make LSTMs particularly appropriate to a wide range of applications, including time series forecasting and natural language processing. It involves tasks with the integrate long-term dependencies for exact predictions. Such enhancements allow the usage of LSTMs to overcome dependencies of simple RNN, which serve as a basic for more powerful and efficient tasks due to the complex memory mechanism and strict regulation of input-output mapping. LSTMs are ideal for modeling of complicated temporary dependencies. These are LSTM advantages, and next LSTM neural network theory. And systems was in response to the internal flaws of simple RNN, for instance, in ability to identify long-term dependencies. The first problems tackled were vanishing and exploding gradient, which greatly affects the learning capacity of traditional RNNs during backpropagation. The major drawback in using RNN is that when it comes to learning long sequences of data, the gradient of network become extremely small and phenomenal. It is known as vanishing gradient problems. On the other hand, the exploding gradient problem, in which those gradients grow and become very large using unstable, and thus it is for bad convergence. Next. We have made a model using LSTM with a time series data. So the time series data we have taken here is the monthly view production in Australia. So for this project, we have demonstrated our initial LSTM implementation for beer production dataset, and this involves a high number of processing and architecture designs. The first step of data pre-processing phase involves in this research aimed at normalizing the month production values, keeping them within the range of 0 and 1 using min-max scale. In order to provide the network with scalable inputs, to further split the dataset by following the percentages were adopted. For this, we have split the data into 67% for training and 33% for testing. And the number of data could be 314 for testing the data and 15314 for training the data and 154 data points for testing the data. One of the major strategic choices made during this design of model was to use a look back period for 3 months. In essence, the design involved in the use of 3 months moving window is to forecast the next month's production. So we have made the input shapes as 314 data points, 3,1 for training and 154 3,1 for the testing data to capture the temporary relation of the data input. For the model architecture, we have included two LSTM layers. So for each of the LSTM layer had 50 neurons, as all the layers were selected in a way that they're ensured to model complexity and the time required for GPU were reasonable. So coming to the first LSTM layer, it was followed by dropout layer of 20% dropout rate to reduce overfitting of networks and improve the generalizations. The last layer consisted of only one neuron of a dense layer. Since we have a regression problem, estimating monthly production values. Another training process was involved with a batch size of 32 and training up to 50 approx. It takes the help of Adams optimizer, and it involves mean square error as the loss function. This state of arrangement help out in achieving intended learning objectives besides keeping steady training force timings. And for neural network design, so based on the observations that are made during first preparation of the networks, a detailed change of network architecture was carried out to improve its capabilities. The most important modification were to raise the number of LSTM layers to 3 and to double the neurons per layer to 100. So initially we had 2 layers, 2 LSTM layers and 50 neurons per layer, but now here we are changing LSTM layers to 3 and we are doubling the neurons from 50 to 100. These two alterations threw considerable new capacities into models for picking up more involved temporary dependencies. The length of input sequence was increased to 5 months to help the long-term dependencies in the production. So for which we have split the data into 80:20. So the model has large amount of data to practice on while the testing data is aggregate. A simple attempt was made to improve the training configuration here, where the batch size was 64, which is opposite to it before, and total number of epochs brought down to 100. So this dropout was adjusted to apply to all subsequent layers in the past LSTM layer and was set to a 20% rate for greater consolidation of regularization throughout the network. Each of these modifications was made deliberately to enhance the model's temporary complexity and exclude overfitting via multiple regulation options. Mm, neural network design. So in this, the observations was made to initial rollout a radical redesign of the network architecture was made in order to optimize it. The largest modifications were making the number of LSTM layers to 3 and we have increased the neurons and we have also altered the training samples to testing samples ratio 4 is to 1 and increased the range of learning samples while at the same time ensuring that we still have both the testing set. Now we have created a LSTM layer and we redesigned the LSTM layer. Now we need to compare the both LSTM layers. Comparing and analyzing the layers models. So examining the performance of both LSTM implementation indicated a leap of performance improvement in the redesigned model. The improved architecture seems to have steadily lower training and testing losses and a reduction in testing mean square error from the initial architecture. The RMSE on the testing data was also found out to have a drastically reduced, which meant improved prediction accuracy. These improvements can be attributed to several factors, such as the problem of increased training complexity due to the larger LSTM layers and more neurons, and the ability to capture patterns beyond the specific time horizon given by the input sequence, and the fact that using the one dropout layer allows the better model regularization is the comparison of both both the networks which we have discussed in part 4 and part 5. So where we can see part 5 has like the redesigned model has the lesser loss in everything. So we can the redesign model is worked great. So coming to the conclusion, there is a large scale study depicts the development and modification of neural networks for time series prediction and emphasizes its application in the area of production of data analysis, evaluating the evaluation from simple RNN to optimized LSTM architectures also support the revelation of the fundamental issues and drawback in the neural network architecture. The marked improvement in forecast accuracy is to redesign LSTM model affirms that the choice of the model architecture and tuning of hyperparameters are crucial determinants in the performance of the forecast. Possible future work can be done through incorporating bidirectional LSTM or explore attention mechanism that can be possibly enhance the forecast accuracy. It also shows how the model is redefined in an interactive manner and show the hypothesis that simpler models are easier to implement is true. From the findings of this research, it is possible to make a number of generalization for the application of the time series analysis in production forecasting and other fields of activity. The enhancements in forecasting accuracy were based on the architecture optimization presented in the work offer a perspective for similar uses in production planning and industrial analysis. So based on this experiment was performed with the higher batch size of 64 and 100 epochs. An actual dropout was applied to all the LSTM layers and then said that this mechanism is applied through the network. But the 20% rate only after each LSTM layer. These modifications were made to enhance the model's ability to time-dependent patterns while addressing multi-fold regularization points without the risk of overfitting. This could be the conclusion. And finally, in the project report, we have limited the information for all the parts from the report, and we have limited and we have adjusted it right here. This is about my project. Thank you.